Swayam Prabha. Digital India. Educated India.
Hello everyone, in today's class we will discuss sequence to sequence modeling. In the last class we discussed RNN methods, advanced RNN methods, LSTM, GRU and so on and so forth. Right, we have seen how gating mechanism can address the vanishing gradient problem. Right, we will see how RNN can be used in the other types of problems like sequence to sequence labeling problems. Right, okay, let's get started. So sequence to sequence models, we are discussing those things which were proposed in 2016, right? Right, so in sequence to sequence model, what is a sequence to sequence problem? A sequence to sequence problem is you are given a sequence and the output would also be a sequence, right? Let's say machine translation, you are given a Hindi sentence and the output would be English sentence. Let's say summarization, you are given a longer document and your task would be to basically generate a shorter document, right? These are all sequence to sequence problems, right? It can be many to many, it can be many to one, it can be one to many and so on and so forth. Many to many sequence to sequence model. Sequence to sequence, the term can also be abbreviated as seq to seq. Okay, so many to many seq to seq problems include summarization, dialogue, right? Many to one, what do you think? Many to one seq to seq problem can be classification or no? Huh? So it's not a sequence to sequence as such, because ultimately you are generating a label, but I mean you can think of it as sequence to sequence. It also depends on the way you map it. What is one to many? Example of one to many? No, speech is a sequence to sequence. Speech generation, music generation. What's the input? Input will be a prompt, right? Or so that is many to many. What about image captioning? Your input is an image and output is a text, a sequence. Of course, you can say that I can basically flatten the image, make a matrix or whatever, right? That will be a many to many, but high level this is one to many. Okay. So let's look at this machine translation problem for the time being. In a sequence to sequence model, what we do, since there are two sequences involved, input and output, we will use two RNNs, right? One RNN will process the input, another RNN will process the output. Okay, let's say this is the French sentence. I'm not able to pronounce it at all. I don't know French. Let's say this is the French sentence, and you use a simple RNN, right, to encode the sequence, and let's say this is the last hidden state, right, and this is your output. The output, the translated version of this French sentence is he hit me with a pie. Okay, so the last state of the previous RNN will be fed to the first state of the output RNN, and the remaining process will follow. Now, if you look at this thing very carefully, where is the loss we are computing? So we are computing the loss at the output hidden state, at the output RNN. This is the output RNN, right? Now look at the timestamp. So here, let's say when you allow, so this is the input, right? Ideally, the first input of the first hidden state will be a start symbol, right? And it should be able to generate the next word, which is he, right? Now you pass this he to the next hidden state, it will generate something. Last day I mentioned something called teacher forcing, right? What is a teacher forcing? in teacher forcing, I, instead of feeding he, let's say here the model generates C. So ideally I should feed C, and then I will see what the next word is going to be, right? This is a normal process, but in teacher forcing, I will feed the actual input, right? For example, even if it generates C, I will feed he in the next state, right? Which is kind of a cheating, but this is it. I mean, it turned out to be much more effective in at least training the model. During inference, you can't do this, but during training you can do. Okay, so at this stage you will have some error, at this stage some error, and so on and so forth, right? Look at this. So here you have an error J1, error J2, J3, J4, J5 dot 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 J7, right? And the total error is basically sum of this. This is the total error, and you normalize it by the number of output tokens T. Okay, and then when you do back propagation, right? So this loss will affect all the hidden states. This is end-to-end training. This is called end-to-end training. End-to-end training. Okay, so this error will be back propagated, and all the hidden states in the decoder as well as encoder will be updated. So the input RNN is called encoder and the output RNN is called decoder. This is end-to-end training. Clear? Okay, and how do we do this back propagation? We will use BPTT, back propagation through time. Okay, now if you think of this sequence to sequence problem carefully, this is essentially a conditional language model. Why this is a conditional language model? What is it conditioned on? It is conditioned on the input, right? So X, let's say X is the input. Here input is the, in case of machine translation, input is the French sentence and the output is the English sentence, right? So you are basically computing this probability. So this is, now if you think of Y as Y1, Y2, Y3 dot dot dot, so the first probability that you are computing at the first hidden state, right? What is the input there? The input is the final hidden state of the encoder, right? So that is X, but you have already processed the entire input sentence, right? So probability of Y1 given X, the next one, this one, what is this one? This is probability of Y2 given X and Y1, right? And so on and so forth. The last one, the last word will be probability of Yt given Y1, Y2, Y3 dot 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 Yt minus 1 and X, right? So conditioned on the generation, the tokens that you have generated so far and the input token. Okay, so now when we decode this, how do we decode this? During the inference stage, can somebody tell me, let's say the model has been trained, okay, how the model is trained? I think it is clear, right? How the model is trained? We will do teacher forcing, right? And we will compute the loss at every time step, right? And then we backprop the entire loss end to end, okay? And you do it for all the machine translation pairs. Now during the inference stage, what you do, you are given a, now since there are two in RNNs, encoder and decoder, how many weight matrices are there? So in encoder, how many weights are there? There is this WH, right? There is this WE and there is this U. So U is not there in the encoder. U is there or not? What is U? The U matrix was the linear projection matrix, right? That is not there in the encoder, because at the encoder stage you are not predicting anything. So you need a WH and a WE. What is WE? WE is the weight matrix corresponding to the embeddings. And at the decoder stage, what are the matrices? WH dash, WE dash, and U. Okay, and these matrices are trained, are learned during the training time. Remember, the embeddings, right? The embeddings that you are using here are different, because input is a French sentence, output is an English sentence. The embeddings are different, right? Let's say if it is a summarization problem, then the embeddings will be same, because the languages are same. Okay, language is same. Okay, so now during the inference time, what we will do? We are given the French sentence, we pass it to the encoder, right? We will use these matrices. Using these matrices, we will get the final hidden state of the encoder, right? That hidden state will be given to the decoder, and in the decoder, I already know WH dash and WE dash, right? So based on that, I will generate this hidden state, the first hidden state of the decoder, right? And then I pass it through this linear layer U, followed by nonlinearity. It will project it to a 1 million dimensional vector. 1 million is the size of the vocabulary, right? Now, so it will project it to a 1 billion dimensional probability vector. Then you sample one token from the probability, right? And the hope is that the token which has maximum probability will be sampled. So let's say you sampled he, okay, and then you feed here, it will generate heat. You feed. So when I say I feed he to the next layer, what does it mean? It means I feed the embedding of he to WH. This WH dash is the same for all the tokens that you are generating in the decoder. In a greedy decoding strategy, instead of sampling the token based on the probability, I will choose the token which has the maximum probability. I will not do any sampling. Okay, this is greedy decoding. So what is the problem with greedy decoding? The problem is that, let's say if you made a mistake at any point, you won't be able to recover it. Let's say you wanted to generate I hit, so you wanted to generate he hit me with a pi, so you generated he, and then you generated hit, and suddenly you generated A, but you should have generated me, isn't it? You won't be able to backtrack, because it has already been generated. The A will be fed to the next state, and in the next state something else will be generated. This is the problem with greedy decoding, right? Now tell me, what do you think? Like, how do you address this problem? Is it possible to do some sort of exhaustive search to address this problem? So instead of, now think about it, instead of generating one token at a time, right? If I could have generated V number of tokens, what is V? V is 1 million, right? I generated all V number of tokens. Now again, for each of this V tokens that I've generated, I pass it to the next layer. It will generate again V tokens, and so on and so forth, right? V tokens and so on and so forth. Is it possible to do that? It is not possible to do that, right? Let's say if it is possible to do, what would be the complexity? There are T number of timestamps in the decoding state, right? Stage, and let's say V number of possible tokens that you can generate. How many possible branches you need to keep track? V to the power T, right? V to the power T. This is extremely exhaustive. Okay, so how to then solve this problem? Let's not make it that exhaustive. Let's squeeze it as much as we can, and to basically squeeze the entire thing, we'll use something called beam search. Okay, in beam search, what we do, the idea of beam search is very same as the exhaustive search. Only difference is that instead of keeping track of V possible options, I will only keep track of k possible options, where k is the size of the beam, right? It means that instead of generating only one token as we did for greedy decoding, or v tokens as we did for exhaustive search, I will generate k tokens. K can be 5 or 10, whatever you set the value of k. Okay, so at every stage here, let's say I generate k tokens. Now from each of these k tokens I further generate k tokens, and so on and so forth. So complexity is still significantly high. Complexity is still k to the power t, isn't it? But k is much smaller than v, right? And you can decide the value of k. Okay, so now what we do, now think about it. You generate a token here at time t, right? You generate, let's say, k number of tokens, right? Token 1, token 2, k number of tokens here, okay? And from each of these tokens you again further generate k number of tokens, and so on and so forth, right? And then you stop at certain point, right? When do we stop? When do we stop the decoding phase? When we stop? I give a French sentence. When this decoding stage will stop? When it generates a token called EOD. There are two tokens, special tokens, start and EOD, end of sentence or whatever, end of decoding, EOD, right? Full stop basically, right? So this is one way of basically stopping the decoding phase. There are other ways also. So each of these branches, right? So let's say this branch will lead to end of token. This branch will also lead to end of token. This branch will also lead to end of token. So there are multiple branches, right? Each of these branches is called hypothesis. Why hypothesis? Because we do not know which of this hypothesis is correct, which of these branches is correct. Therefore, this is called hypothesis, right? So now which hypothesis I will choose at the end? I will choose a hypothesis whose score would be higher. And how to measure the score? The score is essentially the log probability of the sequence that we have generated so far. Clear? So two things I mentioned. One is the value of k, right? We decide a k, and then every hypothesis will be assigned a score. Okay. Now let's look at example. This is an example. So a beam search of size 2. I start with this special token start. This is the decoding stage, inference time. Decoding stage, inference time, not the training time. Remember this. Let's say the value of k is 2. So I have generated two tokens, I and he, right? And what is this probability? This log probability. How do we get this probability? We will get the probability from the distribution, isn't it? Because we have this linear layer and then softmax, right? We will get the probability from the distribution, and we take the log probability. Log probability is basically we sum all the log probabilities, which is same as multiplying all the probabilities. Now since this is probability, it will range between 0 to 1. The log of this will be negative, right? So all these negative numbers will be added, and I will choose that hypothesis whose value is maximum, which is less negative. Here the score till this point is 0.7 minus 0.7 minus 0.9. Which one I will choose? Which one I will choose? I don't need to choose because the value of k is already 2, right? Let's explore this further. Now from he, the next two tokens can be heat and start, right? From I, the next tokens can be was and got. So till this part, what is the probability? So at this stage the probability is the probability of this plus the previous one, right? So the total probability is minus 1.7. Here the total probability is minus 2.9, minus 1.6, minus 1.8. So out of this, How many will choose? We choose only 2. So which 2 will choose? We will choose the highest one, right? To maximum one. So one is minus 1.7, the other is minus 1.6, right? And then we explore further. So heat will generate further. From heat I will generate A and me. From was I will generate heat and Stark, and so on and so forth. Here again from this 4 I will decide 2, right? Now look at here, this branch is gone, right? Now only I am exploring the top branch. From each of these again I will generate 2, right? And so on and so forth. Again these 2 will be selected. From these 2 I will generate 2 from each, right? This 2 will be selected, and this, right? Let's assume that here after this the EOD is generated. Okay, so among this, which one is the maximum? The maximum one is this one, minus 4.3. Then I will backtrack, and this is the backtracked, right? So I will generate this. The problem here is longer hypothesis will be penalized. Shorter hypothesis will be given more advantage. Why? If it's a longer hypothesis, then you keep on adding multiple minuses, or basically you are multiplying so many probabilities, which will lead to lower probability value. Let's say you had one hypothesis where there are only 2 tokens versus you have an hypothesis where there are 10 tokens. So which one will be preferred? Let's say both these hypotheses were successfully led to a end of token, right? Which will be preferred? The shorter will be preferred because of this one, right? So what I do here, we will normalize the score by the number of tokens it has generated. So if a longer token is generated, right, I will normalize it by the number of tokens. Shorter token again number of tokens. That will nullify this one. Thank you.